This guide for 4 new ALETRO videos is found on ALETRO's YouTube channel, as shown on the hyperlink on the slide. The first 2 videos, just under 11 minutes combined, give a thorough view of ALETRO's 2014 National STEM Lecture Tour. The last 2 videos, about 23 minutes combined, represent those lectures which will be open to questions and answers at the museums and local schools. ALETRO had to be a DBA, the long name Aerospace Legacy Engineering and Technology Recovery Organization, explains what we're all about, but not very usable for conversation. We have recently relocated from Phoenix, Arizona to Boulder, Colorado, and are ready to launch a STEM lecture tour to inspire students of all ages. Our plan is to provide STEM lectures in science and technology museums and schools across the country. Our directors and advisory board members are a mix of retired and still active aerospace technologists continuing to make contributions to the aerospace industry. This STEM, or Science, Technology, Engineering, and Math, lecture partners with the NASA DFRC, or Dryden Flight Research Center, traveling exhibit teaching reaction controls. My name is Wayne Ottinger. My career in aerospace started in 1955 after graduating from the University of Arizona as a mechanical engineer. My early experience included flight testing of jet engines on the first Mach 2 aircraft and the X-15 rocket research airplane propulsion system. For Apollo, I was the NASA project engineer for the Lunar Landing Research Vehicle, or LLRV, and the technical director for Bell Aerosystems on the follow-on trainer, the LLTV. This diagram illustrates the basic physics driving the critical need for earthbound simulation for landing maneuvers, requiring pilots to acclimate to the much higher pitch and roll angles while flying close to the lunar surface with minimum fuel reserves. This, in addition to moving out of boulder fields or craters, provided one of the most challenging piloting tasks in the Apollo missions. This is the same diagram with notations added by the Utah State University Senior Mechanical Aerospace Engineering class, year 2009-2010 capstone design project, design and testing of a prototype lunar or planetary surface landing research vehicle. Shown here are pictures of a helicopter on Earth in a small angle pitch-up maneuver to decelerate its forward translation, compared to the LLRV, LLTV, and the lunar module in much larger angle pitch-up maneuvers in the 1/6 G gravity condition to achieve the same deceleration. This is why it takes focused and extensive training for pilots to get accustomed to these types of maneuvers close to the surface. In 1962, the Lunar Landing Research Vehicle was conceived and designed to train Apollo astronauts to land on the moon, where 1/6 Earth's gravity and no atmosphere, in an era without modern flight simulators. It was a full motion simulator capable of recreating an actual descent to the lunar surface by virtue of 3 analog computers. It was the world's first pure fly-by-wire control system using hydrogen peroxide thrusters as the RCS system. The 3 6-foot-high photo panels shown in this layout and the pedestal with the sidearm controller will be displayed in the Science Technology Museum scheduled for the lecture tour. These will be used at local schools in each Science Technology Museum location, where the NASA Reaction Control exhibit will typically reside for 1 month. The NASA photo boards are duplicated of those traveling with the historic Gemini LLRV space hardware featured in the pedestal display, which may also be available at the local schools pending final arrangements with NASA.
For takeoff, -1 on the H-dot. Hands off for your balance. 15 feet per second. He has the plate. I'm hovering at 99%. Focus vertical.
local vertical. Altitudes approaching 100.
Left side, I think that's 30%. There's about a 9-degree cross.
Okay. Climbing.
Balance is good.
Thank you.
And the wind is reading 25. Clear for landing simulation. Okay.
His altitude is 300 or speed about
2 minutes to JP4, 50%.
Thank you.
Approaching 40% roll.
Okay. Crosswind.
Okay, when our sim switch is on, camera's on.
Okay.
Approaching.
Speed should drop off now then. Sorry.
Okay, now showing a crosswind here of some magnitude. It should be coming forward now.
Okay. Showing 32%.
Okay, everything looks good. Auto throttle looks good.
Okay, gimbal lock is off. Airspeed is
Yellow
30.
way up.
Okay. On back. Airspeed drops below 30. Descent rate's 10. Altitude's 200.
Approaching 40%.
Okay. Airspeed's dropping back 50. Altitude's approaching 100.
1 minute to 50%.
Thank you. Descent rate's 4. Altitude's 100. Descent rate's 4. Airspeed's 5.
Touchdown.
This sidearm controller flew into space on Gemini 6A, crewed by Wally Schirra and Tom Stafford, December 15, 1965. This was the first successful rendezvous mission between two spacecraft in history. Following its mission, the controller was retrieved by NASA engineer Dean Grimm and sent to NASA Dryden. NASA engineers modified the sidearm controller and installed it in the Lunar Landing Research Vehicle, LLRV number 1. With his right hand, the pilot could control roll, pitch, and yaw thrusters with side-to-side, fore and aft, and twisting motions of the sidearm controller. The LLRVs were modified and sent to Houston to train astronauts for landing on the moon. Said Neil Armstrong of the LLTV's value and his landing on the moon in 1969, "I felt very comfortable. I felt at home. I felt like I was flying something I was used to." This is the first of the 3 6-foot-high NASA photo display panels. What problem does RCS solve and why do we need it? Aircraft control surfaces, ailerons, elevators, and rudders lose their effectiveness the higher you go. Why? The atmosphere gets thinner the higher you go, and aircraft rely on atmospheric pressure and speed, expressed as Q, to maneuver, and those control surfaces deflect into the airflow and move the aircraft. At a certain point, Q begins to drop, and no matter how fast you go, the airplane's control surfaces lose their effectiveness. At 100 kilometers, or 328,000 feet above the Earth's surface, there is so little atmosphere there are too few air molecules for the deflected aileron or rudder to redirect an aircraft. You need another way to control a vehicle. Reaction control systems are used to control a vehicle when Q is too low for any other means of control. This is typically space. RCS allows a vehicle to maneuver with small bursts of thrust, to roll, pitch, and yaw, and to make small adjustments while docking with another vehicle. In the absence of an atmosphere, once you start a motion in space, you must stop that motion or it will continue indefinitely. RCS is essential for this as well. This picture shows the pilot's sidearm controller commanding a yaw motion to the spacecraft, and the other 2 axes, pitch and roll, are shown in the diagram. There are different kinds of reaction control systems: chemical, typically reaction jets or thrusters powered by chemicals. They are powerful, quick, and are common in manned spacecraft. They are also limited to their fuel supply. Magnetic torquers or solar sails. These generate force by interacting with a very minute space environment and suitable for satellites or scientific experiments. They are not powerful, but they are long-lasting. And then momentum transfer devices. Those can work independently or with another RCS to control angular momentum of the vehicle and suitable for manned spacecraft requiring large control forces. A subset of RCS include inertial devices such as gyroscopes and flywheels. These often appear on satellites. Hero, or Heron, of Alexandria, believed to be Greek, was a mathematician, engineer, inventor, geometer, and worked with mechanics. Hero designed an aerofoil, a steam-powered device sometimes called the first steam engine. It does no real work and was meant for amusement. Nevertheless, it was a steam jet, a precursor to the reaction control system. Steam, it is commonly termed a jet in the sense that it can be controlled with a valve. The Chinese toyed with rockets as far back as 350 BC, but those were solid propellant engines that could not be shut off once ignited. This is unsuitable for an RCS system. This is the second of the 3 6-foot-high NASA photo display panels. The X-1B was the first aircraft to test a reaction control system in flight, which the NACA flew in 1957. NASA began flying the JF-104 with the RCS in 1959 as a replacement for the X-1B. The X-15 was the first aircraft with RCS as a standard feature, necessary because it flew to space and back. Normally, black in color, though as shown here is the pink ablative coating applied to X-15 number 3, which was then covered by an additional white coating for high-speed flights. Like Mercury and Gemini, and the lunar module that descended to the moon, the Apollo Command and lunar modules relied on RCS for maneuvering and docking while in space. The ISS uses reaction wheels to control attitude and rely on a visiting vehicle for reboost. For ISS, it is usually a Progress, though the Russian modules have an RCS system to desaturate the reaction wheels. Progress or Soyuz fuel is used for the service module or SM system. Like other spacecraft, and like the X-15 before that, flew back to a landing on Earth, the shuttle used RCS for maneuvering. Those thrusters were vital for docking with the ISS. Satellites tend to rely on non-chemical RCS for several reasons, one of which is the inability to maneuver once the propellant is exhausted. Hubble uses reaction wheels to control altitude and rely on a visiting vehicle, the shuttle, for reboost. It needs a system that does not impart vibration. This is the third of the 3 6-foot-high NASA photo display panels. Green propellants. Traditional propellants such as hydrazine are highly corrosive and extremely toxic. Green propellants are less toxic and less polluting. Green propellants are easier and safer to handle, making it possible to use them around people. In addition to the environmental benefits of green propellants, also bring economic and schedule benefits by reducing the hazards of handling fuel and thus speeding ground processing time and lowering launch costs. Among those propellants considered green are hydrogen, hydrogen peroxide, methane, ethane, oxygen, and nitrous oxide. Space Launch System, or SLS. NASA's Space Launch System, a new heavy-lift launch vehicle, will provide humanity a new ability to reach beyond Earth orbit. The SLS will carry the Orion Multipurpose Crew Vehicle, or MPCV, as well as important cargo, exploration equipment, science experiments, and other essentially needed payloads for voyages into our solar system. Representing the largest launch vehicle ever built, more powerful than the Saturn V rocket credited with launching the notable Apollo missions. The SLS is aimed at opening new chapters of human exploration. The Orion crew vehicle houses the astronauts on the mission. A reaction control system on Orion is essential. It allows the MPCV, or the Orion, to maneuver and dock with another vehicle in space. In much the same way as the Apollo command module and the space shuttle before it, Orion will use a collection of RCS thrusters, or 24 in all, located strategically around the vehicle for control of the vehicle's three axes: pitch, roll, and yaw. As a NASA consultant in 2008 and 2009, I advised a trade study team on the preferred options for a new free-flight earthbound trainer for lunar landings using current-day technologies and hardware. This photo was taken at the NASA Johnson Space Center in Houston as we were viewing the mock-up of the proposed Altair lunar lander as part of the now canceled Constellation program. In the words of Neil Armstrong, 6 crews landed their lunar modules on the moon, each landing in widely different topography. Was performed safely under the manual piloting of the flight commander. During no flight did pilots come close to sticking a landing pad in a crater or tipping the craft over. That success is due in no small measure to the experience and confidence gained in the defining research studies and in the pilot experiences and training provided by the LLRV and LLTV. This LLRV rollout photo was taken when I was 31 years old during my assignment as the NASA plant representative during the design fab of the LLRV in the Bell plant in Niagara Falls, New York. I was able to use Walter Dornberger's office during contract negotiations as he was working just half-time then. This is the only surviving LLTV, as the number 1 and number 2 vehicles were lost during checkout flights by the NASA pilots supporting the astronaut corps after maintenance or configuration changes. I like to brag to my grandchildren and great-grandchildren, now 45 in number, about my X-15 movie appearance in the control room for the early part of the 1961 X-15 movie, Mary Tyler Moore's first movie.